Hi everyone and welcome to this video. Last time we have used neural networks, in particular feed-forward neural networks, and we have been using genetic algorithms to train these neural networks. All of this has been implemented in BASIC and the program has been running on the Atari. This is a supervised learning method, so this time in this video we are going to focus on something different, which is an unsupervised learning method. In particular, we are going to focus on the method known as reinforcement learning. So to understand what this method is, we are going to quickly discuss about the concepts of agent and environment, states, actions and rewards, and a policy. Of course, I will go just through the tenets so that one can make a program and understand the program that I'm going to describe in this video. But if you are interested in knowing more about reinforcement learning and not just the tenets, I suggest to have a look at this book here from Sutton and Barto. You can consider this as a very good reference to reinforcement learning methods. The problem that we are going to focus on today is a robot that is going through a maze, and the robot has to understand how to get out of the maze without us telling it how to do this. The robot or agent will be trained on a modern machine in QBasic, and then the agent train will be running on the Atari 800 XL. So all of these will be in BASIC, but we will have two different codes this time, one that is running on a normal PC and the other that is running on the Atari. As always, I'm reporting here a few links so that if you want to duplicate the results that I'm going to show in this video here, you can. And as always, I want to conclude here this introduction by thanking you guys for being here, for watching these videos, for subscribing, for leaving comments, and for sharing those videos as well. This is very, very appreciated. This is very encouraging, so thank you for keeping doing this. So what is a reinforcement learning method? As we just said, this is an unsupervised method, and in practice this is a method that is defined by the problem you want to solve. In this particular case, the problem we want to solve is practically a problem of an agent that has to explore a maze, but the agent doesn't know anything about the maze and doesn't know how to explore it, so it's going to learn it. And one peculiarity of reinforcement learning methods is that the agent is going to do this by interacting with the maze. So imagine that you have this agent or robot and it wants to explore the maze. And so what it does, it's going to make a few moves, it's going to perform a few actions, and it's going to practically interact with the maze. So once this happens, an observation of the situation is performed, and the agent gets a state of the maze and a reward from the maze. And the reward, in a way, you can think of this as practically a way to tell the agent what it should do. So the reward is going to tell the agent, okay, if you are out of the maze, you have maximum reward, and if you are still not out of the maze, then you have a smaller reward. Also, in terms of the actions that the agent can perform, we have to bear in mind always that the action happens in a trade-off between exploration and exploitation. So the agent starts to build the history about its exploration of the maze, and sometimes wants to use what it knows, and sometimes it just wants to make a random move to explore something that it didn't know before. So all of this happens through practically playing the game of the maze many times, so that the agent can actually build this historical of the actions and of the rewards, and eventually build a strategy also known as a policy. So once the agent has a policy, then the agent is considered to be trained, and the agent now is capable of going through the maze and going out of the maze. to provide more details about what we are going to implement, I'm showing this figure here that should clarify a little bit what we want to implement. So the maze is essentially now our environment, and the agent is represented by a robot that is going through this environment. And the environment is not exactly the maze that I have just shown in the previous figure, but it's a simplified maze, which is the one that you see here in black and white with dots and walls. And in practice, the problem that we consider here is to have a robot that starts on the top left corner of the maze and has to exit through the bottom right corner of the same maze, of course. And the way it's going to do this, it's like this. The robot is going to play this game many times, and it's going to do this through a trade-off between exploration and exploitation. So exploitation means essentially it's going to use what it knows from its previous exploration of the maze. And with this information, what the agent is going to do is to create essentially a policy. Before we can create a policy, though, we also have to create a list of allowed states that the robot can take. So in practice, it means that we have to know what are the positions and the actions on that position that the robot can take. And we are going to provide this list of allowed states by providing essentially free information. We will have a position, we will have the action that the robot wants to take on the position, and we will provide a value that is a Boolean that can be true or false. So true would mean that the robot can perform the action at that position or in that state, and false would mean that if the robot is at that position or in that state equivalently, it cannot perform that action. And this will become practically a table that is going to be created by exploring the maze the first time. Then through the use of historical data that the robot is going to collect, a policy table can be created as well. What do we mean by a policy? So a policy, let's say it's an equivalent way to say a strategy. And a policy in this case is going to be again a table. The table will have practically the state and then the reward. So in practice, what we mean here is that if the robot is in state 1, for example, it has a high probability of getting reward number 1, and so on. Now, once the robot has played many games and has tried to escape the maze for many times, we end up having these two tables, which can be saved in files. And in practice, what we are going to do at the end is to take these two files, migrate them on the Atari 800 emulator or on a real Atari 800 if you have access to one. And then in practice, these two files are going to be utilized as practically a way for the robot or the agent to run on the Atari and solve the maze. So in practice, the training of the agent is going to be performed on a modern computer in QBasic, and then the robot performing its exploration, or let's say solving the maze, is going to be implemented on the Atari. So it will run on the Atari. So now we are going to go through the code. So let's start from the training phase. Let's focus on the QBasic code that trains the agent. So the very first thing that I'm going to do is to show the code itself so that you can stop this video to focus on any detail, and then I will explain how the code works. Now that we have seen the code, let's try to explain a few parts. So the very first thing here that you see is we are telling QBasic that every array will have an index that doesn't start from 0 but starts from 1. And then here we are declaring a few functions that we are going to define on the bottom of this code. What you see here instead, this is a definition of Boolean values because BASIC doesn't have any concept of Boolean values, and we are defining a true and a false very easily. The false will be 0 and true value will be 1. Then in this list that you see here, essentially we are defining a bunch of global variables that we will need through the code. And what we start to do eventually is that we start to have the user settings. The very first one is referring to the total number of episodes that the agent will use. So in this particular case, by episodes we need the game of the maze. So, and practically this is the number of games that the robot will perform. We also have a max move here. This practically tells you how many moves the robot can tell before we stop the game, because sometimes the robot will not be able to go out of the maze, so we have to fix a limit. And then we have a few more variables. So alpha, you are going to understand what it means once we go through the update of the policy. And these two values here are pretty simple to explain. So practically we say that the robot initially will be in a trade-off between exploration and exploitation. So what we are saying here is that at the beginning, in the very first games, the probability that the agent will explore randomly the maze will be 95%, and then we will reduce by this quantity every time we approach a new game. So in practice what happens is that we will have a high probability of random exploration at the beginning, and then the robot will step by step practically use an exploitation or whatever it has gotten from the exploration, from the previous exploration of the maze. Then we define new arrays here. These are arrays that we are going to use to create an history of the robot, and in practice we will provide here every time there will be an index, this will be an index for the move. So we will have the first move, the second move, and so on. And we will here, we would practically save the position or the state of the robot, and here we will save the reward that the robot has gotten in that particular state. Then of course this is the index for these arrays, which starts from 1, and then step by step we are going to increase this. What we define here is slightly different. These are practically variables that we define to create the maze. So we will practically say that the symbol 0 corresponds to an empty position of the maze. The symbol 1 will correspond to a wall in the maze, and the symbol 2 will be essentially the robot or the agent. And then here we start to define the actions that the robot can take. So the total number of actions will be in this particular case 4, because it can go up, down, left and right. And what we do here in this part here, we actually define those actions. So for example, if we take action up, we will have practically a decrement of 1 in the X direction, and we will have no decrement or no increment in the Y direction. So practically this will correspond to the robot going up in the maze, and in the very same way we define these other actions. We can now proceed with the rest of the code. So for example, here we define the dimensions of the maze. In this case it is 6 by 6. And here we define a few global arrays that are going to define the maze, and practically the allowed states that we are talking about just earlier. Eventually here we call a routine that we are going to see, which reset the maze, and we call another routine here that initialize the maze. And because we want to start from scratch, we are going to reset the table of allowed states by practically saying that any state and any action of the robot is equal to false initially, and then we will update this table when the robot is playing. The initial position of the robot is the top left of the maze, the top left corner, which corresponds in our particular case to the position 1, 1, which is saved in these two variables here. And what we do here is that we initialize the robot position in the maze, so the maze in position 1, 1 will have a value that is equal to 2, which corresponds to the robot being in that particular position. Here we reset another variable which corresponds to the number of steps that the robot has taken. This will be very useful once we are creating the historical actions and moves that the robot has taken. So if we now proceed further, here we initialize the policy or the strategy table, and the way we do it is very simple. We practically provide a random number that is going to be between 0.1 and 1. The reason we don't go below 0.1 is because we would have practically in exploration or in exploitation problems. So we practically start from something that is above 0. And then here we construct the table of allowed states, which is very simple to do. I'm going to explain this routine in a while. So now here we have the main part of the code, which is the reinforcement learning loop. This is the main loop that you have in the code. And in practice what we do is this. We have a for loop that is going to go from 1 to the number of episodes or the number of games that the robot is going to play. We show it on the screen. And then for every game we reset the position of the robot in the top left corner every time we start the game. Here we initialize the maze, so we give the position of the robot in the maze, we reset the steps, and we say that this variable game over is false. We are going to use this variable so that every time game over is true, we stop the game. Of course, the reward, since we are starting the game, the reward is 0. Then we have a while loop here that you see on the screen here, and this while loop is actually the game. So in practice, if the game is not over, we are going to go through this loop many times. And the very first thing that we are going to do is that we provide the position of the robot or the state, and according to the state of the robot, we want to know what an action could be. So it's this routine that you see here, select action, actually select an action, and it does it either randomly or by using what it knows so far from the previous exploration of the maze. We are going to explain this in a while. Then we update the maze because now we want the robot to perform that action, which means that it's going to have an impact over the maze, and we have to change the maze accordingly. Eventually, after the move has been performed, we update the reward, and to do this we use this function here that I am going to explain. We update the state history as well, and then we check if the game is over. If the game practically is over, we go out of the while, and if it is not over, we just continue to loop through the while structure. Also here what we do is we check that the number of steps of the robot doesn't go beyond the variable max moves. If this is the case, essentially we give the position of the robot at the end of the maze, and we also provide game over being true, so we go out of the while loop. Here what we do is that in case we are interested, we can also print the maze while the robot is playing, which can be very useful, because if you do that, what you will see is that initially the robot is playing very randomly, but the more it plays, the better it becomes at this game. Here, since we have, let's say, we have ended the game, so we can reset the maze, we can reinitialize the maze, and before we start a new game, what we do is that we ask the robot to learn from its previous experience in the previous game. Of course, I'm going to explain this routine. So if we now proceed further, I will not explain in every detail this part of the code, but practically what it does is that it takes what the robot has learned from the many games that it has played, and eventually it replays the game. But rather than going through a trade-off between exploration and exploitation this time, it's just going to select a greedy action, so the action that provides the maximum reward. And by playing in this way, in practice, we will be able to see if the robot has learned anything. This part here is going to run on the, let's say, on the code here, so on a modern computer, but this part also will be the part that will run on the Atari. So I will explain this in more details once we go through the list of the Atari program. Eventually, once all of this is done, of course, we save the matrix G, which corresponds to the policy or the strategy, and we save the allowed state, or let's say the allowed action tables as well, because this is what we are going to need on the Atari. So we are now ready to go through the subroutines. The very first subroutines that we have here is reset the maze, so it practically gives the maze every position equal to 0, and the initialization of the maze provide the walls, so this is what you see in this part here. Then we have another routine which is called print maze. I think you understand what it does. In particular, if the maze at position XY has a value that is equal robot, we will print the string R. If we have a wall, we will print this hashtag value here, symbol, sorry. And if we have an empty position, we will just print a dot. This is very simple to understand. Then, in order to slow down the visualization so that we can follow what the robot is doing, we let's say, ask the computer to delay for 1 second, so that practically every second we see one move of the robot, and all of this becomes understandable. Also, we can now go through the routine that is constructing the allowed states. So the very first thing that it does, it resets the table of allowed states by practically saying that any state and any action is practically not allowed. And then this is where we actually provide the right values for the allowed state array. So the very first thing that we do is that we go through every single position of the maze, and we check that that position is different than a wall. If this is the case, then we can do a few things, and what we do is that we take every single action that the robot could take in that position, and we check if this is an allowed position or not. So this for loop with the n index is practically going through every action that the robot can take, which is up, down, left and right, and it checks if those moves are allowed in that particular position. If this is the case, then it provides a value true to the array allowed states. So this is pretty simple to understand, but this is the way we construct the table of allowed states that we are going to use on the Atari. So now we can go through this other routine, which is the update of the maze, and you are going to understand this is not very complicated. So we provide an action to this routine, and then we get the position of the robot. And in the maze where the robot is, we are going to provide now the value empty because the robot is leaving that position. And then we update the position of the robot, as you can see here, and then we update the maze as well. So at the new position of the robot, the maze will have the value 2, which correspond to the agent being in the position X, Y. And then since we are updating the maze, we also update the number of steps that the robot has taken so far in the maze. We can also now go through this other routine that is quite simple to understand, and this is the routine of update state history. So what it does is that it updates the state history of the robot. The way it does that is pretty simple. Every time you call it at the state history index, it's going to give the actual position that is provided in the routine here. So if we provide, let's say, state X and state Y, this is what we use to update the state history. Then we provide the corresponding reward, and we increase the index of the array so that we can go to the next element of the array every time we call the routine. And now we have a very interesting routine here, which is the routine learn. And this is where practically we update the policy or the strategy table. And the way we do it is not extremely complicated. So what we do is that at the end of a game, we have now a history of the game. So we can use this state history to create this policy. And the way we do it is by using this formula here, where by increments we are updating every time the value of G. So G is going to provide, in a way, the reward that the robot would take if it had, let's say, the position that is provided to G. Also, what we do here is we reset the state history every time the robot has learned, so that we can practically start a new game and we can create a new history of the game. And what we do here also is that we reduce the random factor by a value that is equal to delta random factor every time the game is concluded, so that in practice, game after game, the robot use less random exploration and use more of the history that it has learned. This routine here is very simple to explain. We are just saving the matrix G so in practice we create the file that the Atari is going to use, and in the very same way it happens for this routine here that is saving the table of allowed states that the robot can have. This is the other file that we are going to use on the Atari 800. So now here we have a bunch of functions that we are going to explain quickly. So the very first one here is this function here is allowed move. So if you provide, let's say, the state of the robot, which is the position in this case, and you provide also the action that the robot would like to take, in practice this function is going to provide you a true or a false, and it provides true in case the action can be performed at that position, and it's going to provide a false if this is not the case. The way it does it is pretty simple. So if the position is after the update, let's say, or after the action, if the position is outside of the maze, then of course you provide the value false because the robot doesn't have to go out of the maze. And then it also checks if the robot is on an empty space. If this is the case, so if the robot is on a position empty or it's on the same position, in practice this is an allowed move, so we return the value true, and if this is not the case, we practically provide the value false. So for example, let's say the robot has taken an action and ends up being on a position where we have a wall. This is not allowed, so we return the value false. And now here, this function here is a different one, which checks if the game is over or not. So in practice, what it does is very simple. If the robot is in the bottom right corner of the maze, then in practice you provide the value true, because now the robot is in the final position or on the exit position, and if this is not the case, you always report false. Now we also have other functions. So we have one that provides the reward. This is also very simple to explain. So in practice, if the robot is in the position, in the exit position of the maze, so we practically provide a reward that is equal to 0, but if it is not there, we provide a value that is -1. So in practice, these -1s are going to be accumulated once we are updating the reward, and this provides a very, very big value with the negative sign. So in practice, what we want to do is, ideally, we would like to have a total reward that is equal to 0, which is practically impossible. But in practice, what we would like to have is to have a total reward that is not too small. So what we will do is that by using the reward, we will be able to understand what is the best policy for the robot. We can now go through this other function, which is very simple to understand, although it is very long. So it selects the action for the robot provided a position. And what it is going to do is very, very simple to explain. So here there is one part that is important. So we shoot a random number, and if this random number is smaller than this random factor, we are just going to explore the maze in a random way. And if this is not the case, what we do here is that we perform a greedy move. So in practice, what the robot is going to do here is going to find what is the action that provides the highest reward, and it's going to perform that action or that move. So the function eventually select the move and return the move to the code that is calling that function. The last function here that we have in the QBasic code is when we want to select the greedy action, which is not extremely different from the final part of the previous function, because in practice what we do here, we select the action that provides the highest reward. This select greedy action function is a function that we are also going to implement in BASIC on the Atari, so I will explain this function in more details once we go through the Atari code. One final thing that I would like to do, of course, is to run this code. So I'm just going to run it and show you what happens. And in practice, what you see in this window is that the robot is playing many games very, very quickly, and then it's showing you how it can now perform the game, knowing all the history that it has known through explorations of the maze. And as you can see, the robot went from the top left corner, which was the entry of the maze, and went to the right bottom corner, which is the exit of the maze. So we are now ready to go through the basic code of the Atari. So let's see now the Atari code. The very first thing I'm going to do is to show the listing by typing list and then enter. so that you can have a look at the code and you can stop this video whenever you want to have more details. But I am also going to explain parts of the code. So the very first thing that we are going to do is to list from lines 3 to 8, where we have a bunch of declarations. So the first thing that we do is we set the number of steps of the robot being 0, and then we define on line 5 the dimensions of the maze, which are 6 times 6 in this particular case. We also define the value for true and false, which is the same as the previous QBasic code that we just went through. And then we define a few arrays by doing some memory allocation. We define an array for the maze at line 6, and we define arrays for the policy on line 7, which is called the array G, which is two-dimensional, and the array of allowed states, which is the array S here, that is again two-dimensional. NA on line 8 is equal to 4, which is the total number of actions that the robot or agent can take. And then still on line 8 we define the arrays AX and AY, which in practice are going to contain the actions that the robot can actually perform. So if we now go ahead and we go from line 9 till line 45, this is what we get. So in this part of the code, this is not very complicated. We are loading the matrix G that was saved by the QBasic code. And one thing to note though is line 30, where we are actually using the value that has been loaded from the file g.dat. And on line 32 we have a remark where we define Gij equal a random value between 0 and 1. So whenever we don't want to use the matrix G that has been pre-computed, but we want to use a matrix G that is random, we just have to comment line 30 and uncomment line 32, which we are going to do once I show the examples. So if we now go further and we go now through lines 48 until line 92, you get another part of the code which still deals with files. And what this part of the code does is pretty simple to explain. It's going to load the pre-computed file known as states.dat, which contains in practice the allowed states. So this is not super complicated to understand. It's just loading values from the file. So I will proceed with another part of the code. So if we now go, for example, from line 95 until line 120, this is where we define the actions. And if you go through that part of the code, this is practically just a duplication of what we have defined in QBasic. So to make sure that the actions that the robot is going to perform are exactly the same ones that we are using in the training phase. So if we now proceed further and we go from line 125 until line 150, this is what we get. This is a definition of the maze. We start to define the maze. Here we reset the maze, so everything is set to 0. And then we can go further and see lines from 155 until 179, where here we actually define the maze. So we are telling where the robot is going to be, we define where the walls are going to be, and we define where we have practically empty places or empty positions where the robot can walk. If we go further, and we go line 180 until line 260, So here this is the part where the robot is playing the game, and this is very similar to what we have seen in the QBasic code. So in practice on line 195 we have this while loop that ends at line 250, and practically this while loop will continue until the game is over. So the variable over is set to false on line 190, and then there will be a check to make sure that the game is over or not at the end of the while loop. So now if you go on line 205, here you see that there is a go sub. So go sub to line 300. There we are going to select the action, and then we update the maze according to the action on starting on line 208. So this is what happens until on line 225 we check if the game is over or not, and the way we do this is practically by checking the position of the robot. We also update the number of steps that the robot has taken on line 227, and then what is also interesting is line 235, where you clearly see that if the number of steps of the robot is bigger than 16, then the robot stops playing. And then on line 240 there is another thing that is interesting. You have a go sub to line 532, which is where we show the maze. We are going to see those parts of the code. So if we now proceed further and we go from line 300 until line 330, this is where we select the greedy action, and as you can see, this is not very complicated to explain. What we do here is practically we do a loop through the actions that the robot can take. We check if these actions are actually allowed or not, and if one of these actions is allowed, then we go on line 40, where essentially we are going to check the reward. 400, sorry, not 40. So now if we go from line 400 till the end of the code, which is line 405, this is exactly what you see. So in practice, what these two lines are going to do is to check practically what is the value, the reward or the maximum value corresponding to that state and that action, and then the action is set, the variable action is set to the value n, which correspond to the actual action. So if we now try to run the code, we have to modify a few things first. So I'm going to go from line 9 to 45, and I want to do what I want to do here. I'm going to put a remark here, and I'm going to remove the remark here. So what I want to do in practice is I want to have a random policy, and this is what you see now in the code. So if I now try to run this code, you are going to see that the robot tried to explore the maze but doesn't perform very well. So let's run it. And as you can see here, it's trying to do a few things. The agent tried to explore, but you see it's not doing very well. So if we now modify the same lines that we have modified earlier, and we practically use the pre-computed value for G this time, so this is what we do here, and we put a remark here so we don't use any random value anymore. Yes, so the code now is perfect. If we run it, this time the agent is going to practically use pre-computed values of G, where by pre-computed values we mean the values that were computed by the QBasic code. So if we now hit enter, you are going to see that the robot performs drastically different. As a matter of fact, you see that the robot is going straight to the end of the maze, which was what we would expect. This concludes this video for today. As always, thank you so much for your attention and for being here, and I hope to see you in the next one.